So let's start. So let me just clarify one question which was asked last time. So when we calculate the total cross section for the say for this E plus E minus to mu plus mu minus, then we find that there's a funny fact. Yeah. Let me just write down. So then there's a factor like this. So m prime square E square divided by m square E square, and then times something else. Okay, times something else. And so there's funny feature that this factor seems to blow up when the E is equal to m. Okay, so if you decrease E to the value of m, and then this seemingly blows up. Okay, but of course this never happens in the real situation. In the real situation, because this mass is much larger than this mass, so the upstairs will go to 0 before this blows up. So that's why people never cared about it. Okay, including myself. But you can ask the question: suppose the electron is more massive than the muon, and then you will reach the zeros of this first before you reach the 0 of this, and then you will see something blows up. Okay, then it's curious. There's a very simple mathematical reason for this, and the reason is that cross-section is defined. Remember, the cross-section is defined to be defined to be the divided bundle over the flux, and the flux is proportional to 1. It's the density times the velocity, and the density is the same. It's just one particle per volume, and then the velocity goes to 0 when this is precisely comes when the velocity goes to 0. Okay, because when the velocity becomes very, very slow, then your flux becomes very slow. As small, then this becomes big. So mathematically, that's the reason why this becomes very big. Okay, when you take the velocity goes to 0. But still, it is a little bit funny, I should admit. So when the velocity is equal to 0, of course it's unphysical, because when the velocity is 0, they just never scatter. Okay, so this divergence is never an issue. But you can ask the question: why physically somehow when you decrease the v, and somehow the cross section should become bigger and bigger, and mathematically it's due to the flux, just due to the way the cross section is defined. But I also mentioned before that the cross section is supposed to measure the effective area of the interaction, and then why should that depend on the velocity? Okay, and so this aspect that I don't have a very good explanation, but this is the mathematical reason for it. Okay, good. Yeah, so this is just clarify the question of the last time. Okay, so then we talk about crossing symmetry. So let's consider two processes. One is the E plus, E minus goes to mu plus, mu minus, as we just discussed, with the Feynman diagram going like this. So this is the, okay, so this is the E minus, E plus. This is the mu minus, mu plus, okay? And so there's also another process. Let's consider another process, which is E minus, mu minus, with mu minus going to E minus plus mu minus. And the Feynman diagram for this is given by this. Okay, so this is the E minus, and mu minus is the initial state now, and this is the E minus, and this is mu minus. Okay, again, only one diagram contributes. Okay. So if you compare A and B, you can see that the the diagram for B is essentially the diagram for A if you view it sideways. Okay, if you view it sideways, and then you see this goes to that, and then this becomes final state, And the final state coming out, the E plus essentially become E minus, and this is just become that. Okay. So the difference between these two is that the E plus, so E plus in initial state of A then goes to E minus in final state of B, okay, in final state of B. And similarly, the mu plus in the final state of A then become the mu minus in the initial state of A, of B. Okay? So, yeah, so we essentially, you see U plus, essentially you take the E plus going to the other side, become E minus, and then take a mu plus going to this side, become mu minus. Okay? So essentially you just exchange that. So, so now let's label the quantum numbers. So suppose let's call this P1, R1. So this is call it P2, R2, and call this one, say call this one K1, S1. So these are the polarization, and this is K2, S2. And now similarly, I label here by P1, R1. Label this one by P2, R2 bar. So this is for the antiparticle. And so this one would be the K1, S1, and then this would be K2, S2 bar. Okay. So now if we look at this map, so it's like in A, in the process A, we take this to be initial state P2, R2. If we replace it by minus K2, S2, okay, minus K2 means that yeah, so this one E plus now become the final state. So so this is the so from the momentum direction, this is the going in, and this will be going out. So we need to change the sign. Okay, we need to change the sign, and similarly the K2 for S2 for K2 S2 bar. Yeah, and then go to minus P2 R2. Then we get, if you make this placement, then we get the process B. Okay? We get the process B. So you just make the replacement, and then those replacement, then the process in A will go to those process in B. So for scalar, so suppose you forget about those polarizations. If we consider, had we talking about the scalar particles, there's no polarization. And then this just trivially. So for scalar with them, we just have trivially we can just do the replacement. You can just trivially see that then the amplitude for the process A with P1 minus K2 and the K1 minus P2, and then will be just equal to the amplitude for the process B with P1, P2, K1, K2. Okay, so you just rename your momentum of your process A, and then you will just get the essentially the amplitude for 2. Because the only thing you need to do is just exchange the name of the momentum. Okay. So then will be trivially the same. But for fermions, we should worry about also look at the wave function associated with external lags. Okay, so in A, so let me just write down those wave functions explicitly. So in A, so the P2, R2 bar are associated with the wave function is to be V bar R2 P2. Okay, so this is for the E plus. And so the K2 S2 bar are related to VS2 K2. Okay, so this is related to the mu plus. Okay, so according to our previous rule. But in B, the corresponding the wave function for these two, so the K2 S2, so the corresponding one is the one you want to exchange is US2 bar K2. So this is corresponding to E minus and the P2 R2, then that's corresponding to UR2 P2 mu minus. Okay? So now you see, even when you make the label change, suppose you make the label replacement from here to replace by that, you're not going to change the wave function from V to U. Okay, so the wave function actually is different. So similarly, this does not this does not work if you have fermions. Okay, if I have fermions, because the wave function changes. It changes from V to U. In this case, here case again also V to U. Okay. But actually, this is another problem if we consider unpolarized spin sum. Actually, still works. Okay, for unpolarized. So if you have an unpolarized situation, remember we need to sum over all the spins and consider m squared, sum of all the spins. Okay. So now so that will involve this one sum with itself. For example, when you sum over all the R2s, then we will have something like this. Okay, so for example, we need to sum over R2, then we will have a combination like VR2 P2, that's the calculation we did before, and VR2 bar P2. Okay? And then this one will give you just minus IP2 slash plus M of the electron. Okay? And now you can just do the replacement. Let's just do the replacement, the P2 basically by minus K2. So if you do the replacement, then that goes to minus I slash K2 plus still an electron mass. Okay? And then this is the same as the sum over S2 US2 K2 US2 bar K2. Okay? So despite that their wave function are the different, okay? So the wave function, but after you do the spin sum, okay, they actually get the same answer. Okay? So this is the same as the minus this one. Okay. Okay? So in this case, after you do the spin sum, so each replacement of momentum. So in this case, just give us a minus sign. Okay. When you calculate this spin sum, m squared. Okay. But now since we need to replace two of them, okay, so 2 minus sign is a positive sign. So we conclude that the sum over spin ma squared evaluated at P1 minus K2 and K1 minus P2 is the same as the sum over spin, the amplitude for B squared evaluated at P1, P2, K1, K2. Okay, so there's a simple relation between the amplitude square when you do the spin sum, and you just need to rename the momentum. Okay, rename the momentum. Good. Any questions on this? So for unpolarized amplitude, okay, so we still have this very nice relation between these two processes. Okay, if you calculate one of them, then you don't need to calculate the other. You can just immediately get the answer. You just change a few momentum. Okay, change a couple momentum. So, but if you consider polarized amplitude, okay, so the story is now much simpler. Now you do have a problem because now you have, say, now the wave function are different. Okay, but nevertheless, you can choose a different basis. Okay, by choosing appropriate basis, we can still directly relate equated amplitude. Okay. Okay, you can still equate the amplitude. Okay, so I will not go into there. Okay, but it's possible. Say you choose a basis of V2 and the U2 and the U, and then somehow you can relate them to each other. Okay. So this relation between the amplitude of A and B, so this is called crossing symmetry. Okay, yeah, let me just call this star. So star is called crossing symmetry. So calling it a symmetry is actually a misnomer, because this is not a symmetry. Okay, this is just a relation between the amplitudes of different process. Okay, so this is not a symmetry. So the symmetry should be put as codes. Okay, so this is just express the relation of one amplitude to the relation of another amplitude. Just relation between the amplitude of one process to the amplitude of another process. And this relation, the relation comes from a fundamental fact, comes from a very simple fact. Okay, so if we consider this fermionic field psi, so psi can play two roles. It can either annihilate Remember, psi is called A plus B dagger. Okay? So it's called A plus B dagger. So you can either annihilate an initial particle so that's the A part, or can create an initial antiparticle, or can create a fellow, an antiparticle. Okay, so let me just elaborate. So if we have A, when you act on this side, can you only have if you have a particle in the initial state, then A can annihilate that particle. But if A acts on the left, A becomes a dagger, and then that creates an antiparticle. Okay. So yeah, so in such a process, X plus A goes to Y, and then you can just, so this relates to, so X and Y are some combination of particles, and then this just relates to X goes to Y plus A bar. Okay? Y plus A. And so here just X and Y, some collection of particles. And A A just some particle. Okay. Okay. So just confirm that. Okay. Good. Any questions on this? Yes. Yeah, E minus or mu. Yeah, just that you have you have one field for E, you have one field for mu. Yeah. Yes. Sorry? Sorry, say it again. Like the process X and A combined to Y. Yeah. And we think of it as first X equals to Y and A bar, then A bar and A like annihilate or do something like that. Yeah, heuristically you may, but it's simpler than that. Yeah, it's simpler than that. Yeah. Yes. Yeah. So that's why you have to change the momentum. So it's some momentum for this process corresponding to some momentum for that process. Yeah. It's related. We have to switch the initial and follow momentum. Yeah. Just it's not say these two processes are the same. It's just that this process for one set of momentum have the same amplitude as the other process for some other set of momentum. Yeah, there's a relation between them. Other questions? Okay. So now let's consider another important process called Compton scattering. So Compton scattering played a very important role in the early days of physics, and in showing that actually yeah, this is one of the early experiments to show that the macroscopic world is governed by quantum mechanics rather than classical mechanics. Okay. So now let's consider how to calculate the physics for this process. So Compton scattering is a process. You have a photon hit the electron, and then you get another photon, and then you get another electron. Okay. And so we can draw the Feynman diagram for it. So one Feynman diagram is the following. Let's just imagine you have a fermionic trajectory. So you can imagine at some point there's a photon come in. Okay. So this is the electron line. So electron line is the arrow is the charge line. So the photon line, the arrow should be understood just as a momentum. Okay. And then you emit another photon. Okay, as a Fallot state. Okay. So this is the Feynman the simplest Feynman diagram for this process. But actually, there are two diagrams because you can also, for this electron line, you can also first emit a photon and then absorb a photon. Okay, you also have that. Okay, so you have two, and these two processes are independent, not the same. Okay, so now let me put some label on the diagram. So again, the fermion is P1 R1, so electron initial state, and let's put its final state to be K1 S1. And the photon, let's put its initial state to be P2 alpha. So alpha now is the polarization for the photon. And so call it alpha 1. And then this one, let's call it K2 alpha 2. Okay? And then let's label this index to be nu and this index to be mu. Okay? Because the photon carry a vector index. Because the polarization carry a vector index, so there's mu here. And so I always imagine the momentum is coming in for the initial state and the momentum come out for the final states. Okay. And for this diagram, it's the same thing. So I have P1. So I label the P1 R1. So this is the P2 alpha 1. And so this is K1 S1. And this is K2 alpha 2. The only difference is the role of mu and nu is switched. So for the alt neg is mu, so mu now is here. And for this one is nu here. Okay? So nu is associated polarization of the ingoing photon, and mu is the polarization associated with the outgoing photon. Okay. So this is my Feynman diagram. Okay. So this process compared to the one we considered, this E plus E minus 1. So these have some new elements. So that's why this is a good example to look at. So the new element, there are two new elements. First, in this example, we have, so this propagator is a fermionic one. So now we have an intermediate fermionic propagator. Okay? So, and the momentum for this one, so let's call it Q1 equal to K1 plus K2. Say this is P1 plus P2. But this one will have a different momentum. So here, let's call it Q2, will have, so what's the momentum for this one? If I draw the momentum going to the up. Yeah, so let me put it here. So what would be the momentum of this one? Let's call it Q2. Can Can you read the momentum of this intermediate line from the diagram? Yeah, it's P1 minus K2. Because you have P1 come in, and then K2 come out, so that's the momentum. Okay. So in this one, you have P1, and then you have the P2 come in, and then this is P1 plus P2. Okay, so the new element is that now we have a fermionic propagator as intermediate state. Okay. And the second new element is now we have photon in the external state. Okay, so this is a new element compared to this E plus E minus example. Okay. So now let's, but still, using our previous rule, we can immediately write down the amplitude. Okay, I think I may not have enough space for this. Yeah, let me try. So let me start from here. So the amplitude, again, the I times the amplitude. Yeah, this I is not important, but nevertheless, let me just write it down. So the amplitude is given by. So we follow. You see, we follow the fermionic line. So here, there's one fermionic line, okay, and so we should follow that fermionic line. And then then we also have the photon polarization. Okay, so let's first write down the photon polarization. So for this photon final state, then we just have epsilon mu alpha 2 star. So K2. Okay, so remember for the photon in the final state, we need to put the star. And also remember the mu is associated with the photon in the final state. And then we have epsilon nu for the initial state of the photon, alpha 1, then K1. Okay, so this is the photon one, okay? Photon polarization factor. And now we need to write down the, so these two factors are the same for both process. Okay, for both process, we are not changing the external photon state. Okay, so these two factors are the same. Okay. So now, and now the rest. So now let's look at this diagram and follow this fermionic line. Okay. So we start with here and then going backwards. So we just have U bar S1 K1 for this electron in the final state. And then we have fermionic propagation, and then we have this vertex should be minus IE gamma nu. All this order is important because they are all matrices, okay? They all have spinor indices. And so this is a matrix. And then we have this fermionic propagator, which is the minus 1 IQ 1 slash, so here IQ. So I just write down the fermionic propagator, minus m plus I epsilon. Okay? So I did the final state, intermediate propagator, and then I have another vertex, and now it's new. And then I have the final. Okay? So that's that diagram. Okay, that's the diagram. And now for this diagram, we do the same thing. And then plus. So the final state again is the same. It's the US1 bar K1. But now here you have IE gamma nu. So now the order changed. Okay. And then you have the photon, then you have this fermionic propagator, which is IQ2 slash plus m minus epsilon. And then you have my IE gamma mu. from here, and then you have the final state, UR1, P1. Okay? Okay? Yes? Yeah.
But if we were working with bosons, it doesn't matter. It seems like the real difference is not like the kinematic difference of like which one gets absorbed or emitted. It's the fact that we have this vector that describes the dispolarization for the photons, right?
No, just these are just two inequivalent Feynman diagrams. Inequivalent.
But that's because of mu and mu, like because they don't, right? When you're writing out the Feynman diagram.
Even not for the even they're not vectors. Still, they're inequivalent diagrams because the momentum here is different. The momentum here is different. Yeah. So they're still inequivalent diagrams. Okay. So these are the amplitude. So again, we look at unpolarized cross section. So unpolarized cross section. So let's look at the unpolarized situation. Okay, so again, we need to average over the initial spin and sum over the final spin. So here, now the difference is now we need to average also over sum over the index for alpha and for alpha 1 and alpha 2. So alpha 1 and alpha 2, they only have two polarization. So again, you get when you average over the alpha 1, you get the factor of 1/2. Okay, so still we get just factor of 1/4. Sum over all the spins of m squared. So this is just the same as sum over, say, alpha 1, alpha 2, R1, R2, okay, m squared. Okay? And each index take value 1 and 2, okay, because the photon also only have two polarizations. So now I will not do a complete calculation of this, okay, so you just square it. So you use the trick, and you use the, you just square it, and then you just try to calculate it, okay. And now to calculate this guy, now we need to use some more tricks, okay. So I will just explain the what are the tricks needed to, new tricks needed to compute this guy. And we will not actually do a calculation, okay, do a genuine calculation. So the new elements we need to use. So a few new tricks in order to do this. To do the calculation. So the first trick is how you treat this fermionic propagator. Okay, it's how you treat the fermionic propagator. So we can just rewrite. Yeah, so this is the inverse of a matrix. Okay, so we can just do the say when we have a propagator like this. Okay, slash plus m plus epsilon. This will not worry about epsilon because the downstairs is level 0. So this is the same as ik slash plus m k squared plus m squared. Okay. It's just because the familiar relation we used before, that ak slash plus m and ak slash minus m is equal to minus k squared minus m squared. Okay, so you can just, then the inverse of this matrix is just given by this matrix. Sorry, I think here should be minus sign. So inverse of this matrix just given by that matrix. Okay. So, and then you can use this to simplify. Then you can use to simplify that expression a little bit. Okay. So this is first thing used. And the second thing used is when do the spin sum so for fermions, for spinors, we use the same trick as before. As the one we used for the last example. But for photons, there's some new elements, okay? So now let's discuss how we treat the photons. So now I treat photons. And the way to treat the photons actually involves some important physics. So let me explain a little bit how we do that, okay? So now if you look at the structure of this amplitude, okay, so let's focus on one of the photons. Say, let's look at this the fellow photon. Okay, so the polarization have the following form. Say let's just look at one of the photon. It doesn't matter. Say let's look at this one, initial photon. And then the amplitude, then you have this. Then the whole amplitude is a scalar. Okay. So the amplitude then has the structure that I have epsilon nu star or nu alpha times m nu. Okay, just say this is the polarization, and the rest I just call it m nu because the index has to be contracted. Okay. So now I do the spin sum. So if I now sum over nu to the spin sum over the alpha, and then I just have alpha equal to 1, 2. To the spin sum relevant for the alpha, I just have alpha 1, 2, and then I have epsilon nu alpha star, alpha nu alpha, mu star, alpha nu alpha, and then I have m mu star, and I have m nu. Okay, I just take the square of it. Okay. So now to do the spin sum involving, look at this object. Okay, I need to look at this object. So remember. So do you remember what is the sum of this object? Yeah, exactly, the transverse projector. Okay, it just because of the physical photon polarization is projected to the transverse space. Okay, so this gives you the transverse projector. But now I claim, okay, so if you do the alpha 1 and 2 mu alpha star nu alpha, so this gives you the transverse projector. But now the claim, but transverse projector is a little bit awkward to work with, okay? But the claim is that actually I can replace the sum over alpha equal to 1, 2 by actually sum over alpha for all polarizations. Okay? So now when I sum over all polarizations, so if I sum over all alpha, then now do you know what is this? Do you remember what is this? You just get eta min mu. Okay, and this one is much simpler. Okay, so now the claim. Okay, so now the claim is that we can just simply replace this sum by eta min mu. Okay, we can replace this by eta min mu. So this is the claim. Okay, so this amounts to the following. So this is equivalent to the following. So if you look at the difference between these two, so now if you look at the difference between the alpha equal to sum over 1, 2, and the alpha sum of all here, so the difference, in other words, we claim that sum alpha equal to 0 and 3 epsilon alpha star mu and alpha mu alpha m mu to be 0. Okay, so the difference between the two is just from sum 0 to 3. Okay, so in other words, so if I write down this explicitly, okay, so this corresponding to so this corresponding to 0 epsilon mu 0 m mu square is equal to epsilon mu 3 m mu square. Okay, so this claim is equivalent to this claim. Okay, so these two will cancel each other. Yeah, the reason the equal here is because the signature, the zeros component, there's a minus sign. Okay. So it tells you that the sum of these two actually will cancel each other. Okay. So now let me remind you how we choose the polarization. Yeah. Now let me try to prove this fact. Okay. It turns out this fact is actually very important. It contains very important physics here. Okay. So do you have any questions before I do that? Okay, good. So now let me try to show this is true. Okay. So let me just remind you of a convention. Is that m mu 0 is equal to just 0, just 1, 0, and mu 3 is equal to 0, and then in the direction of the k. Okay, it's in the direction of the k. Okay. And the epsilon mu 1, 2 will be orthogonal to both of them. Okay? Be orthogonal to both of them. Okay. So now to see this equation, let me call this equation star star. So let's consider just a general physical process. We can actually make a general statement. Okay, not just restricted to that particular example we have here. So let's just consider some general process. So you have a bunch of initial states and go some final states. Okay, but imagine one of the initial states is a photon. is the one we are interested here with polarization K alpha. Okay, with polarization K alpha. And so now the amplitude it just become mu, and then this is the same, okay, as you have some final state, and then you have some initial state, but within the initial state there's a K alpha state. Okay, there's a K alpha state corresponding to the photon. Okay, but now remember, which we discussed in your homework, okay, so that's the purpose of to put it in your homework, that the final state for K alpha, which defined by transverse polarization, is only a representative in the equivalence class of states. And within this equivalence class, they are rated by this called null states. Okay, so they are so we can shift it by a null state. The physics will be the same. So now remember, the null state is like a gauge transformation. So the null state corresponding to and this process corresponding to you change your initial you change your polarization to that corresponding to a null state. The null state the feature is that its polarization is proportional to the momentum. Okay, so that's how we yeah, remember we showed that, yeah, because this is like a gauge transformation. Okay, this is like a gauge transformation. And we also discussed the reason this is an equivalence class, because when you shift by a null state, the overlap between the null states to any state is zero. Okay, to any state is zero, and so you can shift by a null state. So the fact that you can shift this by a null state, your physics is the same. So now use this equation to here. So this implies so this implies that M mu K mu must be zero. Okay, M mu and K mu must be zero. Okay, and this is a very important identity. This is called the Ward identity. Because this is a very important feature which can simplify your calculation a lot. Okay. So the M mu must satisfy the feature that when it contracts with K mu, you get zero. So now remember the K mu is just equal to, so this is on-shell external state, okay, or minus, yeah. Okay, this is the on-shell external state. And then this is just given by, if I take a factor K out, and this is given by -1, and then k, and k. And this is a fact I think you also used in your P set. And this is the same, and this thing is just the same as the difference between the zeroth polarization vector and the third one. Okay, from what we wrote here. Oh, I think I get the sign. Yeah, the sign does not matter very much here. Let me just make sure. Yeah, for my sign, this would be, it's minus epsilon mu. Yeah, that's right. So from here, and then this equation, then it just implies that the epsilon mu 0 m mu is equal to epsilon mu 3 m mu. So that tells you that epsilon mu 0 square m mu square is equal to epsilon mu 3 m mu square. Okay, so this is the one we wanted to prove. Okay, so this is the one we wanted to prove. So this simplifies life a lot. Okay, and so now we show that we can actually make this replacement. Okay, because the 0 and the 3 component add together become actually a law vector, then that actually does not contribute. So now this amplitude, we have 2 external photons. So we can write it as, okay, so for simplicity, so for our amplitude, so back to Compton case, to the Compton story, and then the amplitude then have the form. So we have 2, so I have epsilon mu alpha 2 star and epsilon mu alpha 1, and then this will multiply some t mu mu. Okay, so I call the rest t mu mu. Okay. So now when I do the spin sum, m square, then I can just use this twice, okay, for each epsilon, okay, and then I just get, essentially I just get the, so this I will, yeah, let me just write one more step. I will get alpha 1, alpha 2 equal to 1 and 2, then I have epsilon mu alpha 2 star, epsilon lambda alpha 2, and then, so epsilon nu alpha 1, epsilon rho alpha 1 star, and then I have t mu nu, t lambda rho star. Okay, I just square of this guy. And now I can replace this by eta mu lambda, I can replace by eta mu rho. Okay, so and then this just become equal to eta mu lambda and eta mu rho and t mu t lambda rho star. Okay. So this just makes life much easier. Okay, makes life much easier. So yeah, so essentially these are the 2 important tricks which one need to do in the photon in this Compton case, compared with this story. And once you have these, and this part will be just the spin sum for the fermions. And then that we can just use the same trick as we did last time. Okay, so we will not repeat that. Okay. So now let me just write down your final answer. Okay. And now we can just write down the final answer. So before writing down the final answer, let me just define the frame. So for the Compton scattering, it's often convenient to consider the rest frame of the electron. So we consider photon, because there's no rest frame for photon, okay? So it's often convenient to consider the rest frame of the electron. So let's just consider the picture. We can just consider the rest frame of the electron. So this is often the way, roughly, often also experiment is done. Okay, so you can essentially consider the, say, electron in the matter, and which they don't have much velocity. And then you can have a photon come in. Yeah, so you imagine you have an electron here, and you have a photon come in. Okay, you have a photon come in. So let's call this the incoming axis to be the z-axis. Okay, and then after scattering, the photon, say, will be scattered into this direction. Okay, so let's call this direction theta. Okay, so yeah, okay. So in this setup, so then the momentum of the electron is just the m0. Okay, just the mass of the momentum. Or I erased how I labeled the momentum. And the momentum of the photon, incoming photon, P2, would be just omega 0, 0, omega. Okay, so only have the momentum in the z direction. And then the final momentum of the electron is k mu, k1. So this can be something. Okay, so let's not worry about it. Then for the photon, so photon momentum, final photon momentum. So let's call it, yeah, so this is K2. Okay, so K2, we can parameterize it by omega prime. And then omega prime, then going into the spatial direction, the unit vector in the spatial direction for K2, let's call it n. Okay, so this is the direction of n, which is the theta angle with respect to the z direction. Okay. And then the K1 just can be obtained by momentum conservation from these quantities. Okay. So K1 would be just P1 plus P2 minus K2. So from the fact that the electron have a static mass minus m squared, okay. So you can and then this relation, then the P1 plus P2 minus K2 should satisfy the constraint that this should be equal to minus m squared. Okay? Should satisfy the constraint that from this equation you can actually consolve omega prime in terms of omega. Okay, so we will not write down this equation explicitly. You can easily check yourself. Okay, you can easily check yourself. So you find omega prime is equal to omega divided by 1 plus omega m and 1 minus cosine theta. Okay, so this is the final frequency of the photon, okay, expressed in terms of initial frequency of the photon and the mass of the electron, and then this scattering angle theta. Okay. So now let me just write down the final answer with this setup, and then you find in the rest frame of electron, the differential cross section can be written. So again, the phi direction would be symmetric. Okay. And so let's only worry about in the theta direction. So this can be written as pi alpha square. So alpha square, alpha again is a fine structure constant, divided by m square. And then given by omega prime, the final momentum frequency for the photon divided by omega square, and omega prime divided by omega and omega prime minus sine square theta. Okay, so this is the final answer. Okay, so this is the final answer for the Compton scattering and the cross section. Okay, so this formula actually contains a lot of physics. So let me just describe some of the physics here. So let's first consider the regime that the photon have very slow, low energy. Okay, just low energy photon shining, some light shining on the. So suppose the photon have very low frequency, much smaller than the electron mass. So now, if you look at this formula, so if the initial photon is much smaller than the mass, and then this factor is approximately 0, then you find in this regime that omega prime is actually approximately equal to the omega. Okay, so you find in this regime, the frequency actually does not change when the photon scatter away from the electron. Okay, and then now omega prime equal to omega. So this factor become 1. This factor become 1, and 1 minus sine theta equal to cosine square theta, and this become 1. And then you find that then the d sigma d cosine theta just equal to pi alpha square divided by m square, then plus 1 cosine square theta. Okay. So this is a famous formula more than 100 years ago, or even more. So because this is the classical. So this is called the Thompson cross section. Okay, so this is Thompson cross section derived from the classical electrodynamics. Okay, and so this is a result already known, okay, in the 19th century from the classical electrodynamics. So how people derive this formula in the classical electrodynamics. So in classical electrodynamics, you do it this way. So in classical electrodynamics, so light is believed to be a wave, electromagnetic wave, okay? So essentially it's an electromagnetic wave, so there's electron, or there's an electric field, say with a polarization, and then the magnitude, and then it's a wave, okay? It's a plane wave. Okay? So from the classical electrodynamics, the light is just wave, okay? When you shine the light on the material, the light will scatter. And the physical description of the light scatter is the following. So this is the oscillating electric field. So if you have a charged particle like electron, then will oscillate because it has a charge. under such an E, essentially the electron, so you can approximate the electron in the matter just by a forced harmonic oscillator. Okay, it's a forced oscillation. It's a forced oscillation. So you should have learned in 803 that under the forced oscillation, essentially the electron velocity, electron will have acceleration essentially given by the given by this. Yeah, let me just proportional to the expansion I omega t plus I kx. Okay, essentially just the force acceleration will like this. And then from classical electrodynamics, because this is accelerated motion, this is accelerated charge, and accelerated oscillators in the classical electrodynamic will emit waves. Okay, will emit the electromagnetic wave. So this will radiate. So this will lead to radiation with frequency omega. So essentially controlled by by this acceleration. Okay. So this is the classical result in the classical electrodynamics, that such an oscillator will emit the light with frequency omega. So that's the scattering process from the classical point of view. Okay, from a classical point of view, drive the oscillator, then oscillator will emit. Okay, and if you go from this process, then you precise find this formula. Okay, you precise find this formula. Okay. So in this case, so regarding this, the value of omega okay, the omega prime, the emitted photon always. So in this story, omega prime always equal to omega. Okay, because it's a driven oscillation. Okay. So classically, you always have this. So you always have elastic scattering. So the photon frequency does not change. Okay, and then the equation. So let me call this equation 1. And equation 1 holds. Okay, yeah. And let me call this A and B, so not to get confused. And equation 1 holds. So the classical, very robust prediction is that you always have elastic scattering when you shine light on the this Compton, and then the equation you have this Thompson cross section. But then now in the early part of the 20th century, when Compton did this experiment, and then he observed actually the frequency can be smaller. Okay, so in this formula, generically omega prime is smaller than omega. Okay, but in quantum mechanics, but in general, but in quantum mechanics, we see that omega prime is generically smaller than omega big, because this is 1 plus a factor which is greater than 1. Okay? And in particular, this deviation will become obvious when omega become comparable to n. Okay, when omega become comparable to n. And also, yeah, so this is the quantum mechanics, so you will always have inelastic scattering. So this makes sense because just for momentum conservation, electron, if some photon hit the electron needs to move. When electron need to move, then of course the energy will increase. And then energy will increase, and the omega prime, of course, have to be smaller than omega. Okay? So in the rest frame, electron always gain energy. So that's why in the quantum mechanics, it's always in elastic scattering. Okay. And then the star no longer holds, and this equation 1 no longer holds. Okay. So in the early days, this just cannot be explained using classical electrodynamics. Okay, so this is decisive evidence that actually photon, the light behaves very different quantum mechanically from classical wave. Okay, in fact, this simple fact can be just explained by treating a photon as a particle. Okay, so this is a decisive support that the photon actually behave like a particle. Okay, behave like a particle. So so this to the particle picture of photon. Okay. Okay, so we are out of time soon. So let me just mention one simple application of this. So in particular, let me just mention two small things. So one thing is that if omega is much greater than m, then omega prime divided by m become very small. Okay, so this actually become much smaller than 1. So except the theta equal to 0. Okay. Okay. So so if the initial photon momentum is energy is very big, then actually most of the energy will go to the electron. Okay, and then the final frequencies actually become much smaller than initial frequency. So this is one remark. And another remark. So this is in the electron rest frame, but in a different frame, you will actually get a very different answer. So now let's imagine we have a frame. So in this frame, the electron just sits here, then the photon comes in, okay, in the z direction. Now imagine we boost the system in the negative z direction, okay, in the negative z direction. So the result of this boost is that the photon energy becomes very small, and the electron energy will become bigger and bigger when you increase the boost, okay, because the boost is opposite to the direction of the photon. So you boost more, then the photon energy will become smaller and smaller. Okay. So now imagine you go to a frame which photon have a very small energy compared to electron. Okay. And then this is then in that frame will be a very fast electron hit a very low energy photon. Okay. So this is called the inverse Compton scattering. Okay, so in this case, then the energy in the initial energy in the electron then can be transferred into the photon. Then you have very fast very high energy electron hit a low energy photon. Then you just give a big kick to the photon, and the photon can have very high energy. So this is a very simple effect, but it can have very important astrophysical applications. So this is called the important application in this called the Sunyaev-Zeldovich effect. So essentially, they have the simple observation like this. So in the universe, we have the background we have a microwave background radiation. Okay, the microwave background radiation, the photon is very low energy because the temperature is very low. Okay. But now, if but around a galaxy, so if you're near the galaxy center, so near the galaxy cluster, and near the galaxy cluster, some of the electrons there can have very high energy. And when they scatter on the microwave background photon, and then they can give those microwave background photon a big kick, okay? And then they will, then the photon will get very high energy. So then by looking at the photon spectrum in the sky, look for this kind of hot spot. And then this is a way to detect the galaxy cluster. Okay, then you can just use this inverse Compton scattering that detect the location of the galaxy cluster. Okay. And so it's a very cool application.